much for coming. My name is Liev, and this is Ying Li, and she's going to be talking to us about Carmen Sandiego, I think.
Welcome, Gumshoes, to another episode of Where in Your RAM is San Diego, Python San Diego.py, sponsored by my employer, Rackspace. I'm your host and Acme CrimeNet liaison. The chief appreciates your help and discretion in this matter, but I'll let her explain the situation herself. Gumshoes, we've received a credible threat to the Acme CrimeNet Kate's file server. I got this text from my mother earlier today. My mom thinks that if she threatens my work, I'll have to call her and ask her to stop. She's probably right, but I can't let this sort of ultimatum stand. The next time, she might demand that I make Thanksgiving dinner. My mom's a Python programmer, but I didn't see any Python processes running. I've suspended the server for now and provided you with a memory dump. Find the rogue process, Gumshoes. I need to start the server up again at some point, and I can't have her deleting my files. Chief out. Thanks, Chief. And I guess there's the memory dump. OK, so now we have a 2 GB binary file, a raw dump of whatever was on RAM in the server. It sure would be nice if this giant pile of unannotated bytes were at least split into process regions. Then we can find the part that belongs to the rogue Python process and maybe do something with it. But maybe we can split it ourselves. I mean, all processes are managed by a boss, right? The kernel, which must know their whereabouts and what they've been up to. We just need to find the kernel and interrogate it. But how? Luckily, there's an outside contractor we can employ to hunt through memory dumps for us. It's open source, it's written entirely in Python. And if we give it an accurate description of what the kernel looks like and the addresses of its known associates, Volatility can find the kernel and any processes the kernel can manage. So the first thing we need to do is to build a profile of this kernel. Kernel headers describe the kernel. They define what data structures the kernel uses, what attributes they have, and how big they are. These tell Volatility what the kernel will look like in memory. Luckily, this is easy to get in Linux, which is what the file server runs. They're provided by the Linux headers package for our particular kernel version. For OS X, the kernel headers can be downloaded from Apple, and Volatility has a lot of experience hunting down Windows kernels, so it probably already knows them all by sight. So what about the locations of the kernel's known associates? We're looking for an address book of sorts, called a symbol table. The symbol table has information about identifiers in the kernel code. Information like an identifier's address, which is just a number representing an offset into memory where the identifier can be found. In Linux, the kernel symbol table can be found at /boot/system.map. In OS X, a utility called dsymUtil can be used on the kernel to extract the mapping, like humanely. And again, Volatility probably already knows all the Windows address books. OK, so now that we've built our profile, we can invoke Volatility. We dead drop our profile into a plugin directory, tell Volatility both the location of the dead drop and the name of the profile, and then we point it at the memory dump and tell it what we want to search for. Let's start by telling Volatility to find the kernel and bring it in for a friendly chat. Volatility facilitates the interrogation with an interactive shell command called volshell. This is just an IPython session with some extra context. As you can see, Volatility thinks that it's found the kernel's init task, the head honcho process in Linux, the parent of all other processes. In Windows, this would be the system process, and in OS X, this would be the kernel task. The Linux kernel keeps track of all the processes it's currently managing in a linked list, the first element of which is the init task. So if Volatility has actually found the init task, then it's probably found the kernel, and we can get to all the other processes. So let's use the IPython interface to ask some basic questions, just to establish the suspect's identity. The Volatility shell object is presented as self, and the task currently under interrogation, supposedly init, is an attribute on Volatility shell named proc. We can start off with something easy. Let's say, hey, what are you? Task struct, it answers. And that'd be great if we knew what a task struct was. Well, to answer that, we should understand what the kernel does when a process starts up. We know that init is some kind of Linux process, and we know that the kernel needs some way to keep track of all its processes. So it obviously needs to store information needed to manage the process. And it allocates memory for the process when it starts up, which means it needs to store what memory belongs to what process. The process information is stored in a C data structure, or struct. You can think of structs like Python name tuples, but with declared types for their members. They just group data together. In Linux, this struct is called a task struct. The corresponding structure in Windows would be eProcess, and on OS X, it's proc, but they all pretty much contain the same information, like basic information about the process itself, like the ID, the short name, and the start time. The example displayed here is a Linux task struct. They also usually have some way to access the parent processes, sibling processes, and child processes, and information about the owner of the process, some way to look up the process's open files and sockets, and finally, some way to store information needed to manage the memory of the process. In Linux, it's stored in another structure called the struct. So now that we know what a task struct is, let's return to the interrogation and ask more specific and probing questions, like, what's your process ID? It's 1. That's pretty cool. The init task always has an ID of 1 in Linux. What's your short name? Init. Awesome, identity verified. We've confirmed that this is our suspect. So let's have volatility, a much more effective interrogator than us, ask the suspect what processes it manages. Well, the answer looks a lot like the result of the Linux ps command. There's a list of all the process IDs and short names. Nothing looks super suspicious, though, so let's have volatility ask a different way. This time, the answer looks a lot like the result of the Linux px aux command. This gives us a complete command line arguments for each process, as opposed to just a short name. Still nothing suspicious, though. We should really ask more explicitly. Kernel, do you know about any Python processes? And it looks like no. So that's pretty unfortunate. The kernel was perfectly cooperative and forthcoming with us, though, which means that the rogue process we are looking for must have given the kernel a fake name, and it's lying to the kernel. Looks like this will take some more legwork. So let's have a closer look at the resources the kernel gives its processes and see if we can track down our fugitive that way. We've already examined the process IDs and trees to no avail. Maybe we should look at the open files and sockets. Since the kernel provides and keeps track of this access, it's available to us in the memory dump too. So the kernel has given us a list of every open file accessed by every process. But looking at this, what would we even consider suspicious? One obvious thing would be to see if there were any processes trying to delete the case files, which there doesn't seem to be. But we'd only see that if the process happened to be doing that at the time of the memory dump. Prior access that had finished by the time the memory was acquired would not even show up. Similarly with open sockets, we can look at what processes are listening to what sockets, but unless the chief happens to know her mom's IP, nothing would jump out at us. And unless the process was contacting the server at the exact moment of the memory dump, we wouldn't see it anyway. Okay, so open files and sockets are a dead end. We should have a closer look at the memory resources the kernel provides each process it manages. So let's check out the struct, which sort of looks like this. On the left is what process memory generally looks like. The top is the end of the process memory, where the highest address is, and the bottom is the beginning of process memory, where 0 is. On the right is part of the actual struct declaration. The struct annotates several interesting regions of a process memory. Think of it sort of like sections in a library, like mysteries or science fiction. There's the environment variable section near the top, which has the environment variables the process was started with. Then below that, there's the command line arguments the process was started with. Then there's a stack, which is like a scratch pad for processes. It's where it writes incriminating evidence. This is where programs store function call information, arguments, and return values. It starts at higher addresses, and as more things are added to the stack, grows downward. Next is the memory map section. This is where necessary files like libraries may get mapped to memory. For Python programs, C extensions will be mapped here. Additional file mappings get added to the section at the bottom, so it grows downward like the stack. And looking at it could also give incriminating evidence, like a bad reading list. Then comes a heap, which for historical reasons is referred to as break. This is where dynamically allocated objects go. In Python, that's like every object ever. All of it goes on the heap. So that's really where we want to look for rogue, if we ever find a rogue process. In the next section, we find the data segment, which is the non-instruction parts of the process binary. It's the global and static variables of the binary. For the Python binary, this might be like CPython built-in docstrings. The last region is the executable machine instruction part of the process binary. This is the part of the Python binary that actually runs Python. So if those were like library sections, what's the unit of thing that's being categorized? What's the memory analog to a book? That would be a virtual memory area, which is a contiguous area of process memory that has the same permissions and allowed operations, and that is mapped to the same file. There might be multiple virtual memory areas in a single section. Look at the memory map file section, for instance. But also note that a single virtual memory area covers the environment variables, the command line arguments, and the stack. If you think about it, environment variables and the command line arguments are kind of like the first parameters and function call to the process, so that sort of makes sense. So if the kernel has to keep lists of which virtual memory areas belong to which process, that's just like how a library keeps a record of all the books that its patrons check out, right? And volatility can get us access to this book list without even needing a court order, using the command procmaps. This is all perfectly legal and above board. On a live Linux system, after all, you can see the same list using the proc file system in /proc/pid/maps. The proc file system provides user space, a way to get information about processes without having to make system calls to the kernel. Each virtual memory area has a start and end address, a permissions flag, which specifies which operations are allowed for the virtual memory area. See how each of these three areas have a different set of permissions, even though they're mapped to the exact same file? Speaking of, the virtual memory area has a name, which might just be the name of the file that's mapped, or it might be something like heap or stack. The first virtual memory area in this list is just the code segment part of the file, because it's executable and not writable. The second and third memory areas form the data segment, one being read-only and the other being read-write. So great, we have some virtual memory areas managed by the kernel, but how does this help us find our rogue process? Well, we just have to use the information the kernel keeps about what's mapped in memory to catch one of these processes in a lie. In other words, all the processes managed by the kernel deny that they're Python processes, but do any of them actually have the Python executable mapped as the process code? If so, then that seems like a clear intent to deceive and warrants suspicion. So let's go talk to the kernel again, and we're going to go through its paperwork for its processes with a fine-toothed comb. Each and every process that the kernel manages, which is stored in a linked list that we can conveniently access using the attribute tasks. For each process, we want to identify the virtual memory area that corresponds with the executable part of the process binary. We want to find the code segment. So we go through all of the virtual memory areas for that process, which we can obtain using the function getProcMaps. And we find one whose start and end addresses match the code segment's start and end addresses. That's the code segment. Some processes, mainly the kernel threads, share the kernel's address space and so don't have code segments themselves. We want to ignore those. For non-kernel threads, there should only be one virtual memory area for the code segment. When we find it, we want to print out the virtual memory area name along with the process ID and the short name. And then we can compare what each process claims its name is with what each executable process the process has mapped. And that's weird. There are two processes claiming to be Whoopsie, the Ubuntu error reporter. One's using bin Whoopsie, user bin Whoopsie, which is pretty standard, and the other is using user bin Python. And we are looking for a Python process. I think we have a viable suspect, Gumshoes. Now we need to just build our case. We know this process has been lying to the kernel, but that in itself is not a crime. After all, other legitimate processes also lie about their process name. They overwrite their own short task name and command line arguments. For instance, Postgres does this to show the currently running query, and SSHD does this to show who's logged on. So we need to learn more. What else has this process been doing? We can, of course, ask volatility to interrogate the kernel about this process specifically, whereas we were asking about all processes before. For instance, we can look at the open files this process was using. Looks like it was piping something to dev null at the time of memory acquisition. Not suspicious, but it does indicate that it was probably running in the background. We can look at any open sockets that this particular process had access to. Looks like none, at the time of the memory acquisition. Again, this doesn't mean that the process never made any network connections. It just means it wasn't doing so at the time of the memory dump. Okay, so let's have a closer look at the process binaries. Oh look, it was using the Python library setProcTitle. This is a library that provides an API to overwrite a process name and the command line arguments, so that's how it hid itself. We still don't know anything useful about the process's intentions, though, or what it did before the chief acquired the memory dump. So let's take a closer look at the process's books, namely its stack and heap. There might be incriminating evidence in there. We have the start and end addresses here, so we can just take the file the chief gave us, seek to the start address, and read until the end address, right? So let's start with the stack. There's just one problem. The addresses are really, really big. That would mean that the stack is almost 141,000 gigabytes into the memory dump. But the memory dump itself is only 2 gigabytes. So what gives? Are the kernel's records wrong? Is it in on the whole thing and impeding our investigation? No, actually, no, it isn't. We're just interpreting the addresses wrong. All the addresses that the kernel has given us are virtual addresses, or offsets into process memory, not physical addresses or offsets into RAM. A process sees its own memory as one large contiguous block called the process address space or process memory, and only ever deals with virtual addresses in its own address space. That's the address you'll get in GDB or if you repr an object in Python, and it's usually represented in hexadecimal form. Process memory isn't actually contiguous in physical memory, though. It's sliced up by the operating system into tiny chunks called pages, which are about 4 kilobytes each, could be larger. Each page may be mapped to a different portion of the physical address space, or RAM. Or it might not be mapped at all. Most of a process's address space is not used. You saw the stack's virtual addresses. Those are some large, large numbers, meaning a process's address space is huge, bigger than RAM. So why waste any physical memory on empty space? Even the pages that are used might not be currently mapped to physical memory. They might be swapped out to disk or compressed if the process doesn't need them immediately. Each process uses only the memory that it needs when it needs it. That's what allows many processes, each having a huge address space, to share a limited amount of physical memory. The reason a process can pretend that its memory is one giant contiguous block is that whenever it accesses data at a virtual address, the MMU, or memory management unit, which is part of the CPU, translates the virtual address into a physical address, if the address has been translated before, it might be cached in the TLB, or translation look-aside buffer, instead of being retranslated. If the data at that physical address has been swapped out, it's swapped back in so the process can access it. And all this happens transparently to the process, who has no idea any of this is going on. Volatility can also translate a virtual address into a physical address. We could just ask it to do the translation for us, to get us a stack and heap. And we will do that, but Acme is the kind of organization that provides accountability and oversight for our contractors. Something, evidentiary chain, something, fruit of the poison tree. The point is, we can't just blindly let volatility get us the evidence. We have to at least understand how translation works. In some cases, it might be very simple. For example, on Linux and OS X, the code and data segments of the kernel address space are identity mapped, which means that while those regions are still divided up into pages, those pages aren't scattered everywhere through physical memory. They're laid out in the same order as in process memory. But that's only the identity-mapped regions. The other regions are still sort of scattered. For the identity-mapped regions, the virtual address is just the physical address plus this constant offset, which is only for 64-bit systems. The 32-bit constant is different. If kernel address space layout randomization is supported, ASLR, as it is in newer versions of OS X and the Linux kernel, another random constant also gets added. The random offset helps mitigate buffer overflow attacks by making it hard for critical addresses to be guessed. So the virtual to physical address translation for identity map segments just means subtracting some constant. But what about the parts of kernel memory that are not identity mapped, or non-kernel processes, which are also not identity mapped? Well, by itself, a virtual address is just an offset into the process's address space. But it can also be split into a series of 5 numbers like this that are used in address translation. And this division, again, only applies to 64-bit systems. They're divided up differently and into fewer pieces on 32-bit systems, but the process is the same. So here, only 48 bits are used for address translation. The top 16 bits, shown here in black, are either all ones or all zeros, and they're just thrown away. These numbers, together with some extra information, kind of work like real-world mailing addresses. In most countries, mailing addresses look like this, modulo some formatting. There are multiple descriptions of a location in order of decreasing specificity. Each description in this address lets us narrow down our search. So let's start with the most specific information in the virtual address, the last 12 bits. This is like the apartment number of a virtual address. An apartment number identifies an apartment in a building. the last 12 bits of the virtual address identify a byte in a page. I've marked that byte with an X. The result of the translation is just the physical address of that X, which is the physical address of the page plus the 12-bit offset. But just like there are many buildings in the world, a process can have many pages. So we need to narrow it down. The 9 bits in green is like the street address, which identifies which building has the apartment. The process has a table called a page table that has a list of page addresses. The green bits identify the right page in that list, the page that has the data that we're looking for. Actually, no, the process has many page tables, kind of like how there are many streets in the world named Main. The process does have a table of tables, though, called a page directory. It lists page table addresses, and the 9 bits in purple identify which of those page tables has the page we're looking for. Actually, no, there are many page directories associated with the process. And you probably see where I'm going with this, so let me just spoil the ending. Each process has a table of tables of tables of tables of pages, a 5-level sparse tree of tables. The point is they need to be traversed using the numbers in the virtual address to get to a single page, which we can index into using the last 12 bits. And the intermediate table names, they don't really matter. But we do care about the per process top-level table, the root of the tree. Volatility refers to it as the directory table, and its address is the DTB, or directory table base. And because no one can agree on a 3-letter acronym, the Linux kernel refers to the top-level table as the page global directory, or PGD, whose address is stored in each process's struct. Without this value, without access to the top-level table, there's no address translation. And so the kernel has one too for the parts of memory that are not identity mapped. And the kernel's DTB can be found in the symbol table that we gave to volatility, which it carefully documents here at the end when it brings us tasks for interrogation. You know, for chain of evidence reasons, which is what we here at Acme like to see from our contractors. Okay, so now that we understand address translation and we've satisfied our regulatory oversight requirements, let's ask volatility to get us the stack. We just need to note the start address and tell volatility to dump the virtual memory area that starts with that address. It will find and read every page associated with that virtual memory area and dump them out into one single contiguous binary file, which we can look at using strings, which is a POSIX command that searches the binary file for a sequence of 4 or more ASCII characters ending with a new line or null. Basically, human-readable strings. But there are a lot of false positives, which ends up giving us a bunch of garbage, but also relevant data. Remember how we said that the environment variables and command line arguments were part of the stack virtual memory area? Here they are. The arguments are overwritten to just be whoopsie, but the actual command used to run the process is shown in the environment variable list as an underscore. It looks like it's Python run with no hup, which just lets a process run in the background without dying when the controlling terminal is closed. So now we can do the same thing with a heap, but wouldn't it be nice if we could really get into the process's mind, understand the objects that it was throwing in there? If so, we need to learn to speak its language, the language of Python objects. And that language is C, because this is C Python, which means that Python objects in the heap are C data structures. We mentioned C structs before, that they were complex data structures composed of other data structures, like named tuples. And their members are typed, unlike named tuples, because we don't declare types in Python, yet. And that's all true. But since we want to interpret parts of the heap as C data structures, what's more important to us is that a struct is a packing format for bytes. We need to know exactly what order the bytes appear in and how many of them there are for each struct. For example, this is a struct declaration. Because of the type declarations, we know exactly what it should look like in memory. 8 bytes of data because it has 2 4-byte integers. Any 8 contiguous bytes in memory would fit into this struct. So let's take this snippet of memory, for instance, where the offsets are shown in blue. If we were to interpret the beginning of this chunk of memory at offset 0 as a point structure, we'd end up with x is 3 and y is 2, which is cool. However, the 8 bytes of memory that starts at offset 1 also fit into the point structure. X and y are just really weird. So is this a valid point? Technically, yes, because x and y are integers. But let's say that the point represented by the struct must fall inside a circle of radius 10. In that case, this isn't a valid point, even though it's a valid point structure. We need some kind of validation check to make sure that x and y are correct, independently of whether the bytes are correct. So with that in mind, let's look at how many bytes are in a Python string object. This is a generic approximation of the Python 2.7 PyString object definition in CPython. I'm really sorry, CPython developers, skipping over some stuff because we're racing the clock here. I want to point out a couple of things. First, the state is an enumeration of 0, 1, or 2. We should check for that when we validate the bytes that match the structure. Second, the character array is of size 1, so that's the first character of the string, which is null terminated, and the rest of the string follows immediately after the struct. This is documented in a comment in the CPython source. But volatility can't just accept a C struct like this. We need to translate this description into something that volatility understands, which it calls a V-type, which is basically the same struct definition, but as a bunch of Python arrays and annotated with information about the size of the struct and the offsets of the members. The total size of the struct, as it was declared in C, is 37 bytes. We know that from adding up the sizes of all the members. For example, object refcount was the first member of the struct definition, which is at offset 0. It's of type long, which is basically a really big number. Remember how we said that ints were 4 bytes? Longs are just 8 bytes, which is why the next member, ob_type, starts at offset 8 for the struct data, and so forth. But any sequence of 37 bytes will fit into the struct, whether or not the values make sense. So we need to tell volatility how to validate whether the 37-byte chunk of memory is really a Python string. So we read the string, which is 36 bytes from the beginning of this object, because remember, the first character of the string was the last byte of the PyString object. And we see if it's a valid Python string. The type pointer has to be a valid pointer. Volatility knows all about pointer objects and provides a validity check that ensures that it points to something that's inside the heap. The size of the string also needs to be non-negative, and we can skip empty strings because we don't care about them. And to speed things up, let's ignore really large strings too. The state has to be 0, 1, or 2, as we mentioned before, and the string has to be null terminated, as we mentioned before. And the hash either has to be -1, which means it hasn't been computed yet, or it has to be the actual hash of the string. And we completely ignore ref count because we want to find garbage collected strings. And then here's some pseudocode that tells volatility to brute force search the whole heap by testing every sequence of 37 bytes in the heap for a PyString object validity. So now, when we run it, it will display the actual Python strings from the heap, which includes a ton of Python doc strings. But sometimes you can find useful information, maybe in the form of a garbage collected string. It looks like our process had previously made an HTTP request. Netstat showed no current connections, but luckily, this request is still in the heap, so we can look at it. We'd still see it like this, even if it was made over HTTPS, because this is the raw request before it gets encrypted on the wire. Note the basic authorization header. Basic authorization base64 encodes the username and password, separated by a colon, which means we can base64 decode it and get the username and password for the request. I think this is pretty incriminating, and a message to the chief. I know what you're probably thinking. Couldn't we have just gotten this information using the strings command? And yes, we could have. We could have gotten both the doc strings and the request. So why did we bother going to all this trouble? Well, finding Python strings tells us something about the string boundaries. If that request was not one string but multiple strings, that might have meant something completely different. Strings also only returns ASCII, but with Python strings, we might be able to see bytes read into the process from a file, like an image. Also with Python strings, we could do more filtering around the lifecycle of the string. Maybe we want to exclude garbage collected strings. And more importantly, volatility uses V-types and validation checks to find almost everything: kernel structures, kernel modules, network packets, and on every platform, not just Linux. Usually more cleverly than brute force, too. And now that we understand how this works, we can do the same thing for other Python data structures, like lists and dictionaries and tuples. But unfortunately, that's all the time we have for today. And besides, I think the chief needs to deal with her mom. That's right, detective. I logged into my mom's server with her credentials you found, and it seems like it was returning commands that the Python process was supposed to run on the Acme server. I'm going to block all inbound and outbound traffic to that IP. Now I'm going to call my mom and gloat about how we at Acme have foiled her plans. Good job, Gumshoes. Until next time. So, thanks. For more information about volatility and forensics, I highly recommend the book The Art of Memory Forensics, which made me want to do this talk. I don't actually do any forensics, but it's an awesome and fun learning tool just to learn about memory. There are also 3 fantastic talks earlier at PyCon that go into much greater detail about some subjects that I just barely touched upon, and they're listed here, so please check them out. A full working version of the Python string searching code is up on my GitHub account. It's not brute force. It's much more optimized. And I'll be happy to answer any questions on Twitter or outside. Thank you so much for coming, and thank you for your time.
Thank you very much. That was really great.